What is the shape of sound? This is going to surprise you, that those of you who don't know what the shape of sound is. Most of you probably think that sound is a wave. And it leaves somebody's mouth, say, or it leaves a loudspeaker, and it goes wiggly, wiggly, wiggly through the air. Well, I have to disappoint you if you think that is the case. Sound does not do that. Sound is actually spherical. So every sound that you've ever heard from the moment of your birth has been spherical. Now, here's a nice diagram to demonstrate this, but before we get to the diagram, let me just talk you through the thing. We have vocal folds, little flap of skin that vibrates up and down. What happens in the throat when that little flap of skin vibrates up and down because of the passage of air coming up from our lungs is that a little pearl of sound is created. And here it is, that little pearl. It's a tiny little pearl, spherical pearl of sound. Rapidly expands up our throats, through our mouths. Some of it goes up through our nasal cavities. Two bubbles are formed, one in front of our lips, and one comes down the nasal cavity and joins the main passage of sound out through the mouth. And in a split second, we have this beautiful bubble of sonic energy standing in front of our lips. Of course, it doesn't stand. It actually is moving very fast. But if you can just visualize it statically for a moment. So here it is. Here's the little bubble coming out of the mouth. And on the surface of that bubble is a beautiful pattern. And that is the pattern that represents all the structure in your beautiful voice. And of course, as I said, it doesn't sit there. It rapidly expands away at round about 700 miles an hour. So it's quite hard to kind of visualize, but you can see here a very large sphere that's been drawn, just to give you the impression that it's moving away from the head. And there's a guy standing, blowing bubbles. And you can see straight away, I think you can see on that there's a lot of structure in the bubble. And also, you can see that although the main strength of the bubble is in front of this guy, can you see here that behind, there's another bubble forming behind him. And what actually is happening is, and I'll go into this a little bit more detail later, but the sound is refracting backwards. You know, if you're walking behind someone, you can still hear them talking, can't you? Not as loudly, of course, but you can still hear them. Doesn't matter where you are in relation to that person, you will still hear them. And the reason for that is something in science called diffraction. And it's simply the case that the molecules that are being jostled have reactions. They actually bounce backwards as well. A bit like a billiard table or a pool table. You strike the balls and they scatter, but you get reactions in different directions. So some of the energy goes behind the guy. But what is absolutely true is that about a millisecond after the bubble leaves the mouth, if you were to look straight down, say on my head now, and if you could see this sound bubble, it would be totally spherical about my person. Equally behind, equally in front. However, if the energy in the bubble had color, let's say we attribute the color blue to it, then what you would see on the surface of the bubble in front of me would be quite a deep blue, but behind me it would be rather faint blue. So that's just to give you the illustration that there's more intensity in the direction of propagation than there is behind. So is that all fairly clear? I hope so. Anyway, moving on, we've done this little graphic to show that sound is, as I said, not a wave, but in fact a bubble. And all this is taking a slice through the sonic bubble here, and you'll see these rings. Well, what they are representing are the areas of high compression and low compression within the sonic bubble. So right in the center is meant to be the event, as it were, whatever the event is. It could be my voice, it could be a hand clap, it could be anything. But that's the event right in the center. And then it expands outward in this spherical way, creating areas of high pressure and low pressure. So these are areas where the molecules are all kind of bunched up together, and areas where they're slack, they're not bunched up, they're less compressed, let's say. You don't need to look at the top half, that's just a slice that we've taken off, but the top half would in fact look exactly the same as the bottom half. Now what's this wiggle in the middle? Well, the wiggle in the middle is basically the sine wave. This is what physicists and scientists talk about when they're talking about sinusoidal energy, or they're talking about the sound wave, or they might even be talking about an electromagnetic wave. They still use the same terminology, it's a wave. Well, it isn't a wave. What it is, this is a graph. It's a graph of the energy, of the law of the energy. Let me just explain a little bit more what I mean by that. So if this is the sound bubble at the bottom here, can you see, you might be able to see these little dotted lines going up. Say that one there, for example, if I can hold my head steady enough, that one there is coming right from the outside of the sphere where it's kind of really dark, meaning that the energy is really compressed in the bubble at that point. So look where it goes on the graph. That goes up to this point here, which is the top of the graph, if you like. This is the high energy. So in graphic terms, that's the top. But look here, this bit here where it's like clear, there's not much compression of sound, in other words. If you go up there, you get to the 0 point, meaning that there's hardly any compression at that point. So if you follow that law, as it were, it's a mathematical law. The way that sound propagates is to what is called a sinusoidal law. Now, you don't need to get, if you're not mathematicians, or you were never very good at math, you don't need to worry about it. The main thing to remember about this sinusoidal law is that energy can never go from point A to point B instantaneously. It's impossible. To do that, you'd have to exceed the speed of light, and you can't do that. Well, I don't believe you can. The point is that anything, take a pendulum swinging backwards and forwards, it can't go from this extreme to this extreme instantaneously. It takes time. And as it goes backwards and forwards, so it builds up its velocity, comes to a halt, reverses direction, and goes back the other way. This is a periodic motion, backwards and forwards. And that's what sound does. So as this sound sphere is expanding, it is not only expanding, but the outside of it is kind of trembling. It has a tremor. And it's the tremor which is the sound. Yes? And that is what that graph is all about. It's actually showing us that the law of the energy looks like a wave. And this is where the big confusion has come in science. Scientists everywhere talk about sound waves. They also talk about electromagnetic waves. So I need to put you straight on that as well. There is no such thing as an electromagnetic wave. All electromagnetism is spherical. Exactly the same as sound. It's spherical. Different kind of energy, but it's still spherical. It might be hard to swallow, but as I said, open your hearts, and maybe it'll go in.